Welcome to section 1.3. The topic is lines. And we'll explore the various versions for the equation of a line. We'll find intercepts and slopes of lines, graph lines given a point and the slope, find the equation for vertical line, find the equation for horizontal line, use the point slope and slope-intercept formulas, graph lines, and consider parallel and perpendicular lines. Okay. Most likely familiar to you from your past experience, but we'll go through and develop this basically from scratch and state each of the various versions for the equation of a line, and I'll have a favorite one, and I'll have my reasons for it being my favorite. When it comes test time, I will likely demand that you put equations of lines in my favorite form. The reason for that really is there's only one version for the form of a line when it's in the form that I prefer. Otherwise, there's an infinite number of correct answers to the questions. More of that soon. If we draw a line in the Cartesian plane, the XY plane, then it'll have a certain steepness to it using an informal non-math term, which we'll describe as the ratio of quote unquote rise to the ratio to the quantity quote unquote run. That is, we'll call this slope, which we'll denote with an M, and it'll represent rise over run, quote unquote, again, not very formal, but the idea is, so we move along this line, we'll go over a certain amount and up a certain amount. We'll run and then rise, run and then rise. And this little ratio is what will be called the slope of the line. If it's at a 45-degree angle to the horizontal, we'll go over one and up one, over one and up one. This line in figure 26 here doesn't look quite that steep, so its slope must be less than 1. It runs more than it rises. So we'll quantify this and introduce how to relate this to points on the line here shortly. If the line's horizontal, there is no rise, and all it is run. So it'll be a horizontal line and have slope 0. If the slope M is greater than 0, if the slope is positive, which is the case in this line, then the line is going uphill as viewed from left to right. If you look at it in this direction, it's uphill. You look at it in the opposite direction and it's downhill. So this uphill, downhill, even this positive, negative slope stuff, it makes sense only when you keep in perspective the idea that the big numbers are to the right and up. The lesser numbers are to the left and down. So an idea of uphill and an idea of increasing is very much tied to the fact that we read things from left to right. So if the slope is positive, the function goes uphill. That's exactly what's happening here. If the slope is negative, then the function will be going downhill as viewed from left to right. And what we would have for negative slope is we might run a little bit, but the rise would be negative. So we would go over and down. Rise part would be negative. That would produce a negative quotient. We could alternatively go backwards and up. In both cases, this would lead to a line that goes downhill as viewed from left to right. If a line's vertical, then the slope is left as undefined. Sometimes it's called no slope. I don't like the term no slope. It reminds me too much of slope 0. Slope 0 is a totally different idea. Undefined slope is the term we'll use and the term that the book uses. And the reason for that is there is no run for a vertical line. We get 0 in the denominator if we tried to talk about the slope of a vertical line. So that's the reason it's left as an undefined concept. All right, let's make this more quantified by talking about points on a line. Let P be the point with coordinates x1, y1, and Q be the point with coordinates x2, y2. Distinct points, so some of the coordinates are different. If x1 and x2 are different, the slope m of the non-vertical line L containing P and Q is defined by the formula m equals y2 minus y1 divided by x2 minus x1. It's the change in y divided by the change in x, again, with x1 and x2 distinct, or else we'd have division by 0 and we'd have a vertical line. So you were very much given non-vertical line and distinct x1s and x2s. This is the rise over run thing. If I go back and look at the previous picture, the rise part is how much the y coordinates change, and the run part is how much x coordinates change. So this informal rise over run idea is formalized in terms of this algebraic formula. Change in y's divided by change in x's. A quick little comment. We've taken y sub 2 first in the numerator. Then you better take x sub 2 first in the denominator. We've taken y sub 1 second in the numerator, so we better take x sub 1 second in the denominator. The pair x2, y2 goes together in some sense here, and the pair x1, y1 go together in some sense. Don't mix these up or you introduce a negative sign. So it doesn't really matter which of these you label with the subscripts of 1 or 2, but once labeled, be consistent in the numerator and the denominator. We encountered something like this when we were dealing with a distance formula, and we used x1, x1, y1, and x2, y2s in that setting as well. And I encouraged you to use the subscripts in a consistent way. Turns out it didn't matter then because you were squaring some stuff in the distance formula. But I said, get in the habit of using the subscripts in a consistent way, because later it'll matter, and now it's later. So it does matter. You have to line up the subscripted 2's and the subscripted 1's. You have to line up these 2 points, these 2 numbers, and these 2 numbers, the coordinates of those points, as given in the formula. If x1 equals x2, and we're given these 2 lines, then L is a vertical line, and the slope is undefined. If y1 and y2 are equal, then, well, I guess the slope would be 0 then. And we talked about that a second ago, and we'll talk about it more here shortly. But if the y coordinates are the same, that's not a problem. We can have 0 in the numerator, and we'd have a slope of 0 in that case. What we can have is the x coordinates the same. Well, we could have that on the line, but we can't have that in the formula. So here's a picture to illustrate that, where explicitly we see the run as the change in the x coordinates. It goes from x1 to x2. We've taken that run to be x1 minus x2. In this picture, it's that distance. Right minus left will be positive, so it is a distance. If the function were not going uphill, some of this distance verbiage might have to be modified. For the rise part, it's changing the y coordinates. Yeah, because this line is going uphill, x2 minus x1, that's positive. x2 is to the right of x1. This rise, y2 minus y1, that's positive. y2 is above y1. But if instead of going over and up, we went over and down to find another point on the line, and the line was going downhill, I couldn't talk distances anymore. These parameters, this y2 minus y1, might be negative, for example. And then it's not this distance. It's only a distance when it's positive. But still, that's the quantity that's used in the slope. And as you've seen, distances can't be negative, but slopes can. Slopes can be positive, negative, 0, and there can be the situation of an undefined slope for vertical line, and that's what we have in part B of this figure. So here, can't talk about the slope, can't use the formula, because what's happening here is the X coordinates for both of these points are the same. They've labeled them both X1, it turns out. Not a typo. And I could label this X sub 2, but look at the picture. X sub 1 and X sub 2 are the same. And they went ahead and substituted that in here. So can't use the formula on this because the X1s and X2s are the same. That'll give division by 0. So we've got a situation of an undefined slope here and the situation of a vertical line. Let's look at a couple of examples. Okay. In number 16, they give us a picture, find the slope of the line, and interpret the slope. The only interpretation we can really do is a rise over run description of what we get numerically. But find the slope of the line, no problem. We got 2 points. Let's call this one point P with coordinates x1, y1. There would be -1, 1, respectively. And call this point Q, x2, y2. It's the point 2, 2. So we've got the 2 points. We'll take this definition of slope. y2 minus y1 over x2 minus x1. Okay, y2, there it is this 2. y1 is this 1. So we'll have 2 minus 1. In the denominator, we've got x2. x2 is this 2. It's a different 2. I could color code them or something, but it's this 2. That's the x sub 2. We'll put that there. Minus x sub 1. X sub 1 is -1, and we'll put the -1 here. So potential for mistakes. You're subtracting x sub 1, and x sub 1 itself is negative. So maybe use parentheses, be careful. And this is a straightforward computation, but you start dropping negative signs and you'll mess it up. So be careful with the negative signs. So we've got in the numerator 2 minus 1, that's 1. 2 minus -1, 2 plus 1 is 3, and the slope is 1/3. They wanted a slope. There it is. Interpret the slope. Okay, I'm not exactly sure what they mean, but we'll describe what's going on in terms of this quantity 1/3. The slope's positive, so the slope's going uphill, first off, as viewed from left to right. For each unit 1 that the line rises, it runs to the right by 3 units. Rise over run. 1 unit to the right, 3 units up. In fact, if you'll look at these points and you go 1 unit up, rise, you'll have to go 1, 2, 3 units to the right, run. Rise is 1, run is 3. So we get that little ratio of 1 up and 3 over, 1 up and 3 over, and so forth, to find more points on the line if you wanted to. So there's a computation of a slope, and there's an interpretation of what it means. Instructions here come to us as, plot the pair of points 4, 2 and 3, 4, and determine the slope of the line containing them and graph the line. Actually already got the graph inserted. So, all right, so we'll graph the points, plot the points 4, 2. So now for the solution, we'll go 4 units over, 2 units up. There's the point 4, 2. We'll go 3 units over, 4 units up. There's the point 3, 4. Given 2 points and the fact that you know this is a line, plotting points is a bad way to graph unless you know the shape of the graph and you plot special points. Well, I know what a line looks like. So you give me 2 points and I can find that line. Graphing lines, plotting points is not a bad idea because I know they're lines. Graphing some other things by plotting points, when I know what those other things are and plotting special points and knowing why they're special, that's not a bad idea. We'll see a few more details of that in Precalculus 1, and you'll see a lot of that in Calculus 1 itself. But our problem right now is lines. Having 2 points, I know what the line looks like. There it is. So the points are plotted. There's a graph of the line. They also wanted the slope of the line. Okay, well, we got 2 points. 2 points determine the slope. So here's the graph. Next, we'll use those 2 points, 4, 2, and 3, 4, to find the slope. We might speed this up a little bit later, but for now, let's let P be the point x1, y1, the point 4, 2, and let Q be the point x sub 2, y sub 2, 3, 4. Plug them into the formula. Here's the formula. Let's see, we'll have a y2 and x2 in corresponding positions. That's the 4 and the 3, y2, x2, 4, 3, in that order. So the y2 will appear here, the 4 will appear here, and the 3 will appear here. x1, y1, 4, 2, bottom and top. If I do the x1s on the bottom and the y1 on the top. So I have the 4 and the 2 here. There's an alternate way to interpret this correspondence. These coordinates are together vertically, and these coordinates are together vertically, and in the appropriate places, with the y's in the numerator and the x's in the denominator. Do the subtraction, you get 2 over -1, and the slope is -2. You have an interpretation of that. This line has negative slope, so it's going downhill when read from left to right. Let's look at the graph again. Yeah, it goes downhill. And what the slope was -2. So how about this? We have a rise. Oops, sorry, kids. Oops, excuse me. We have a rise of -2 and a run of 1. Rise -2, so we went up -2, if you like, so we went down 2. But -2 for the rise, +1 for the run. And that's a ratio of -2 to 1. It's negative, it goes downhill. It goes downhill, kind of steeply because the slope is -2. If the slope was -3, it'd go downhill. It'd go downhill more steeply, in fact. They didn't ask us about that, but inspired by the previous one, we'll elaborate on that part. Returning to the notes, let's introduce a new notation, which we may not use a whole lot in here. This might be a notation you encounter in calculus, though. We're going to introduce the Greek letter delta to represent a change in the value of a variable. On a line, the change in x, the run, we've called it quote unquote an informal term, could be represented as delta x equals x sub 2 minus x sub 1. It's the change in the x values. The corresponding change in y, the rise, can be represented as delta y sub 2 minus y sub 1. So the slope of a line then is, slope is quote unquote rise over run. That's the change in x divided by the change in y. We had dealt with it in this form algebraically earlier, and with the introduction of this delta notation, we could write that as delta y over delta x. And the concept here is it's a change in, oh my goodness, there's a typo there. It's a change in y divided by the change in x. These two should be interchanged. So I've got the numerator and denominator wrong. It's the y's over the x's changes in delta y over delta x. So a typo there, I will correct that in the online notes. But it's a change in y over the change in x, delta y over delta x. And this concept of change in will play a role in Calculus 1 very early on. I've made a reference to my online calculus notes, and there's hyperlinks to all this stuff in the online notes. More generally, if x1, y1 and x2, y2 are 2 points on the graph of a function, a little early to talk about the graph of a function, but we can talk about the average rate of change of a function given 2 points. The average rate of change of the function on the interval from x1 to x2, where we've assumed x1 is less than x2, from x1 to x2 implies an ordering, is change in y over change in x, y2 minus y1 over x2 minus x1. And this average rate of change, I think it pops up in the exercises for this section, in which case you're given 2 points and you're calculating an average rate of change. And it's just like calculating a slope. In fact, it is a slope. It's a slope of a secant line to the graph of the function. But numerically, it's just finding this quantity here, and you've got experience with that. when finding slopes of lines. This idea of average rate of change will show up in very early in Calculus 1. We also use the slope and a given point to find a second point and then graph a line. So another interpretation of slope, change in y over change in x, rise over run. Let's look at number 36. Slope of the line is m equals 4/3, and a point on the line is -3, 2. Use this information to locate 3 additional points on the line. All right, they didn't ask us to graph it, I noticed, so we won't. We could. We're about to have 4 points on this line, so that wouldn't be too difficult. But let's take the slope and use the slope and a given point, and I foreshadowed this in earlier explanations. Let's find other points. So we use the fact that the slope of the line is change in y over change in x. And here we know the slope is 4/3. So the ratio, the change in y to the change in x is 4/3. And then we can take, say, for example, the following. We want to choose delta y and delta x such that they're in a ratio of 4:3. How about we take delta x equals 3 and delta y equals 4? Then the ratio of this to that will be 4/3. It's a ratio. I could choose lots of stuff. I can make both of them negative, for example. I think we'll do that next. But choosing delta y is 4 and delta x is 3 satisfies this relationship. For example, there's an infinite number of ways to choose these because there's an infinite number of points on that line, but this is certainly the easiest way to do it. In this case, we get a new point by starting at the point xy, -3, 2, and incrementing x by a change in x and incrementing y by a change in y. So we're going, in this case, since they're both positive, we're going over and up. The up part, the rise is 4. The over part, the run is 3. Substituting in, we have x, y is -3, 2. There's the -3, there's the 2. To this, we're adding, respectively, delta x and delta y. Delta x is 3, there's that 3. Delta y is 4, there's that 4. Do the arithmetic. -3 plus 3 is 0. 2 plus 4 is 6. The point 0, 6 is also on the line. We went to the point -3, 2. We changed the x parameter by 3 and the y parameter by 4. We did a rise of 4 and a run of 3 in that verbiage. Algebraically, that produces this. Geometrically, I go back to my picture with rises over runs and I deal with it from there. By the way, this line is going quote unquote uphill because the slope is positive. They wanted 3 points. Okay. How else could you choose delta x and delta y such that the ratio is 4/3? Well, I could use the same magnitudes of 3 and 4, but make them both negative. And then when we take delta x divided by delta y, we still get -4 divided by -3, which is the same as 4/3. So here's another choice of delta x and delta y. So certainly this is the easiest one. This is probably the second easiest one. It involves nice whole numbers. In this case, we get the new point by starting at -3, 2, like we did before, and adding the change in x and change in y. -3, 2, so there's the old coordinates of the given point. We've changed x by -3, there's the -3. We've changed y by -4, there's the delta y, the -4. Simplifying, -3 minus 3 is -6, 2 minus 4 is -2, and there's another point on the curve. We could start at -3 and -3, 2, this point, and rise. We'd rise -4, actually go down 4, and we'd run -3, actually go back -3, down and back is how we'd approach this if we were to draw a graph and relate it to that, as we did above. They want 3 points. All right, here's an easy way to do it. Like I said, there's an infinite number of ways to do this. We could use delta x is 6 and delta y is 8. Then when we take the ratio, this divided by that, we get 8 divided by 6, which reduces to 4 divided by 3. Let's use that because it's easy. What else could you use? I could make them both negative and they'd have the same ratio. What we really did was take this first one and double both of these. That's where the 6 and the 8 came from. You could triple both of these to get 9 and 12. The ratio would still be 4/3. Here's a way to do it, and these are probably the 3 easiest values to choose for delta x, delta y. Same procedure, start at the point, -3, 2, there it is. Add delta x and delta y, that is add 6 and 8. And this produces 3, 10. And so there's another point on the line. All they asked us to do was find the points. They didn't ask us to go through and graph. Be a piece of cake to graph. We got 4 points on this line. The point they gave us and the 3 new ones that we found. We've got a point and a slope. Well, you know, we use the given point and the slope to find other points. I think you could probably graph a line if you were given nothing but a point and the slope, because you could use the slope to find a second point. And once you got 2 points, you can graph the line. Back to the notes. Shifting gears a little bit and talking about vertical lines. I don't like vertical lines in an algebraic discussion because they have undefined slopes. All lines, as we'll see sometime in chapter 2, all lines determine functions, except for vertical lines. So that's another reason to dislike vertical lines. Along a vertical line, y can be any value and x doesn't change. There's no run in the rise over run stuff for vertical lines. So x doesn't change, y can be anything, x must be a constant, leading us to the equation of a vertical line as a vertical line is given by an equation of the form x equals a, where a is some constant. It's the X intercept. It's everything on that line. X is always a, and y can be anything. To find the X intercept, how do we do that? We set y equals 0. Okay, take this equation and set y equals to 0. Then what is x? It's a, it's always a. So this might seem like an odd thing to say. A is the X intercept. Yeah, okay, that'll determine it. They're just giving you a point on the line. In the way they'll usually present lines in terms of formulas. But this is a vertical line. All vertical lines are of the form x equals some constant. And I don't like them. Since the slope of a non-vertical line, well, I like those. We can talk about their slopes. They have defined slopes. They won't reduce to x as a constant. We can find multiple points on them. We can compute the slopes. We can use a point and a slope to find new points, as we did previously in that last example. But the slope of a non-vertical line can be computed from 2 points on the line. Suppose x1, y1 is a point on the line, and xy is any other point on the line. Think of it as like a variable point. Rather informally here, don't hold me to this, but these subscripts mean we're going to have numerical values for those. They'll either give us numerical values or we'll find numerical values. The fact that they're not putting subscripts on these means you kind of want to think of both of these as variables. It's a variable point. It's a point that moves along the line. You might think of it in that sense. But we've got this point on a line, and we've got this as a representing a point on the line, any point on the line. I think of it as variable, thus any point. And suppose the line has slope m. Then we'll get the relationship m equals y minus y1 divided by x minus x1. I'm letting this play the role of x2 comma y2. We'd normally have y2 minus y1 divided by x2 minus x1. Well, I didn't put subscripts on. Same formula, I just didn't put subscripts on these. I want to think of these as variables and see what this leads to. So there's the very definition of slope. Rearranging this, what we could do is multiply both sides by x minus x of 1. By the way, we won't be dividing by 0 because we were told this is a non-vertical line. Multiply both sides by that, we'd get y minus y sub 1. This would move to the other side. Then we'd have m times x minus x sub 1. That would simplify down to this. And that's our, I guess this is our first form of a line. It's called a point slope form. Point slope form for the equation of a non-vertical line is the following. An equation of a non-vertical line of slope m that contains point x1, x2 is exactly this. Why does that work? Because of that algebra. Because of this picture. Suppose this is point x1, y1, and they've given us the slope. The slope determines that the line looks like this. Suppose x comma y is any other point on the line. How do the coordinates of this arbitrary point relate to the coordinates of this specific point and the slope of the line? Well, the rise will have to be y minus y1, and the run will have to be x minus x1. That's exactly what we had here, and that's what produced this. In this case, the rise is positive and the run is positive. Could you deal with this in terms of both of those being negative? Yeah, I guess we could do x comma y, an arbitrary point. If we put it back over here, we'd start at this point, then we would have to rise a negative amount. We'd go downward, and then we'd have to run a negative amount. We go leftward. In that case, it's still a rise over run idea, but both of those parameters, these differences, would be negative if the point x comma y were back here. The numerator can be positive or negative or 0. The denominator can be positive or negative. It can't be 0, of course, because you can't divide by 0. So these differences, they don't represent distances necessarily. We could put absolute values on them and they'd represent distances. We really don't want them to represent distances. It's kind of another reason I put the rise and run terms in quotes. They could be negative, and they could be negative even in the event that you have a line of positive slope. I'd need rise and run to both be negative so that the quotient turned out to be positive if we had a positive slope. Let's do a couple of examples to illustrate that. Number 42 says, find an equation of the line as given here. This is the same line we did. It's the first example, wasn't it? We had already found the slope of this. Here's what we did. So let me just recycle that. We've got 2 points, P and Q, or x1, y1, and x2, y2. Plug in the numbers, you'll get a slope of 1/3. Remember, we had a conversation about rise 1, run 3. So that's that ratio of 1 to 3. There's the slope. They want an equation of the line. Well, right now we only got one form for the equation of the line, and that's the point slope form. So let's use that slope and one of these points. Which point you want to use? Well, it shouldn't matter because it's the same line. You're getting the formula for a line. So actually, let's use them both and make sure we do get the same thing. So next, we're dealing with a line of slope 1/3. Suppose we were to use the point -1, 1, that point on the left. We have, from the point slope form of a line, y minus y1 equals mx minus x1. M is 1/3. We had that on the previous page. Here we're taking x1 to be -1 and y1 to be +1. The y1 goes here, the x1 goes there. Be very careful with the negative signs again. There ain't much you can mess up. You could lose negative signs, so I'll always be careful with parentheses. You could put the X's and the Y's in the wrong places, but the X's where the Y's go and the Y's where the X's go. So it ain't foolproof, but substitute in, use parentheses, take a little bit of care, excuse me. Simplify a bit and you'll be okay. So the way you will do these on the test, for example, is you will write out the formula, you'll write out what you got, you'll plug stuff in. Excellent. You might make a little arithmetic error after that. No, I could maybe overlook, maybe, depends how frequently it occurs, maybe overlook little minor arithmetic errors on tests, as long as you'll show me you know what you're doing. You're taking this formula and this information and you're plugging it in. Then you simplify. Everybody messes up on arithmetic sometimes. You simplify and you produce this. So there's a point slope form of that line. It's based on this point. But we have 2 points. Suppose you based it on the other point. What if we use a point 2, 2, the point on the right? Let's go back and look at the graph one more time real quick. Going back. Yeah, we had used this point. Now we're going to use that point. It shouldn't matter. They're both points on the line. The point slope form of a line requires a point and a slope. Still the same line. Suppose we use 2, 2, that point, instead of the point -1, 1. Okay, we still got this form of the line. We still got a slope of 1/3. This time, x1 and y1 are both 2. So we'll plug a 2 in for that. We'll plug this 2 in for that, right? The second one, the y coordinate. And we'll plug this x of 1 in there. So we pick up a 2 here and here. Nothing much to simplify in this one. That produces this. Is this the same as this? It better be, because they're the same line. They better be equivalent equations. That's how we described this previously. Well, they don't look the same. You do have the 1/3 stuff going on here, and the coefficient of y is 1, but they don't look exactly the same. Well, let's take one of them. Let's take this one and manipulate it. Let's see if we can't turn it into that one. If we can't, we've probably done something wrong. Let's take the second equation and add 1 to both sides. So let's take this one, y minus 2 equals 1/3 quantity, x minus 2. And let's add 1 to both sides. Why would you do that? Well, then when you take the minus 2 plus 1, you're left with a -1. You get y minus 1 on the left-hand side, which is the left-hand side over here. So the right-hand side better turn into this. So let's see if it does. So for the right-hand side, we've got this. If we were to distribute the 1/3, we get 1/3 x minus 1/3 times 2, that's 2/3. So distribution produces this, plus 1. Negative 2/3 plus 1 leaves us with 1/3. Now we can factor 1/3 out, and we get 1/3 x plus 1. So we've got y minus 1 equals 1/3 x plus 1, as we should have got. So I can turn this second version into this first version. Could you turn the first version into the second version? And guess what? Subtract 1 from both sides. That'll produce a -2 over here, and some arithmetic on this will produce that. So we get the same equation, equivalent equations, regardless of which point we use. So the formulas we get, the point slope form, this is valid. Turns out so is this. They don't look the same, but they are equivalent equations. They have the same solution set. They represent the same line. All right. I wanted to do another one of these. This is one reason I don't care much for the point slope form of a line. It's not unique for a given line. Well, I can manipulate one version into another, but I'd prefer something that always gives me the same version. And we'll have an equation for that of that type before we're done. Next question, find an equation for the line with slope m equals 1/2 containing the point 3, 1. Okay. We got the point, we got the slope. So all we got to do is plug in. Y minus y1 equals mx minus x1. Here's m is 1/2. We'll plug that in. We've got 3 and 1 for x1 and y1 respectively. The x1 that goes over here, the y1 goes over here, produces this. Let's clean it up a little bit. We get y minus 1 equals 1/2 x minus 3/2. There's a point slope form. But like I was saying, I don't like point slope form too much. I've answered their question. I could put this in the box. But let me do some stuff to that, sort of foreshadowing what's going to happen next. We can write this in some other ways. For example, we could take the -1, move it to the right-hand side where it becomes a +1. That's what we've done here. -3/2 plus 1 leaves us with a -1/2. Here's another version of the line. Actually, this is probably my favorite version here. It reads y equals, and you've got this stuff on the right-hand side. That'll be my favorite version of a line. If everybody puts their lines in that version, you do it right, you get the same answer. This has got fractions on the right-hand side. If I was so possessed, I could multiply both sides by 2. That'd produce a 2y on the left-hand side and get rid of these fractions on the right-hand side and produce a 2 times 1/2 x is x minus 2 times 1/2 is 1. It would produce this. This we could further rewrite maybe as either 2y minus x equals -1, taking the x to the other side. Multiplying both sides by a -1, we could also write this as x, positive x minus 2y equals the negative of this, equals +1. Multiply both sides by -1, do some slight rearranging, and it produces that. You can't argue with the validity of any of this. Problem is, I got a bunch of versions for the equation of this line, a bunch of forms. Here's one, a perfectly legitimate, the point slope form based on the 0.31 was this. I like this. We haven't given it a name yet. We will. And I could also write it like this. We've got a multiple of x plus a multiple of y. That multiple is -2 equals some number on the right-hand side. So here's 3 different forms of the same line. To answer their question with the information we're currently presenting, this makes the most sense. But there's nothing wrong with these 2. I like this one. It's unique. The other 2 could be quite different. I could use different coefficients on both sides of the equation here. For this one, we could have used a different point. I mean, this was a natural way to do this one. But any of these 3 are legitimate answers. I like the one in the middle for reasons to be explained shortly. But the same line has potentially a bunch of different equations and can be put in a bunch of different forms. Actually, let me go back to the notes. Okay, that took care of those 2. A couple of other observations. Along a horizontal line, x can be made to be any value, but y doesn't change. There's no rise this time. And so we get y as a constant. The equation of a horizontal line is of the form y equals b. Y equals a constant where b is, say, the y-intercept. It's that idea again. If I plug in x equals 0 to that highlighted equation, what do you get for y? I get b. In fact, if I plug x equals anything in, I get y equals b. So it's independent of what x is. So this is the form of a horizontal line. No rise. The slope is 0. That's what we're getting out of that, which is quite different from vertical lines. The vertical lines had undefined slope, and we got x as a constant. Horizontal lines have slope 0, and we get y as a constant. Somewhat of a generalization of that is the following. In the point slope form of a line, y minus y1 equals mx minus x1, we can rearrange this. We could distribute the m On the right-hand side, that would give us mx minus n times x sub 1 upon distributing. We could take this minus y sub 1 and put it on the right-hand side, and it would become a plus y sub 1. So what we've done here is solve for y. I still want to simplify it some. So that original equation given here can also be rewritten in this form. And this can be modified somewhat. Let's keep the mx term. There's the mx term. And let's call this term here b. Let's call it b. Then this simplifies down to y on the left equals mx plus b on the right, where b is this stuff here, negative mx1 plus y1, negative mx1 plus y1. So what we've done is we've written a line in the form y equals mx plus b. I know what m is, it's the slope. What's b? Can you give a geometric interpretation of this thing? I think you can. Notice the point, x1, y1 equals 0b is on the line where b is the y-intercept. If we plug into this equation, x1 equals 0, plug into this equation, x equals 0. So I'm using these subscripts in a couple of different ways. You plug in x equals 0, and you'll get y equals this stuff here. You'll get y equals b. Plug in, maybe easier, plug in x equals 0 here, and you get b out. You get y equals b. When x is 0, y is b. So the point 0b is the y-intercept. X is 0, and the y value is b, where b equals this stuff here. We won't really use this stuff here computationally very much. We'll use the symbol b a lot. And this leads us to the point-intercept form of a line. The formal statement is the equation of a line L with slope m and y-intercept b is y equals mx plus b. That's my favorite version for the form of a line because there ain't but one way to express it. It reads y equals. We've solved for y. You solve for y in the formula that describes a line, and we all get the same answer. Might have to simplify a little bit to get there, but we all get the same answer. Before, like in the point slope form, there was a bunch of ways to write that. It was dependent on the point you used. This ain't dependent on anything. This is dependent on the line. So we got the same line, we get the same formula. This makes grading stuff easier, makes grading your test easier because there's only one correct answer. This makes, if you're asked this kind of question in the book, this makes you looking into the answers in the back of the book an easier chore. You get one answer, they get the same answer, you are correct. You get one answer, they got something different in the back of the book, you've done it wrong if it's in this form. If it's in one of those other forms, maybe you used one version and they used another version. There's not a unique form for a line in those other versions, but there is for the point slope form of a line. Any line has one representation when you put the line in this form, point slope form. That's why I like that one. So it has very much a geometric idea. You know how to find slopes and you know how to find y-intercepts. You know how to find x-intercepts too, but nobody asked about that in this version of the line. So I go on to explain why I think this is the best form for the equation of a line. We get it in the form y equals. It's a unique form of the equation of a given line, unlike, say, the point slope form. So there might be other versions of a line. We'll introduce one called a standard form as well. That's not unique. So I like this one. We all get the same answer if we all do it right. So it actually simplifies stuff from a teaching point of view, at least. Yet I am obligated to go through these other forms. Here's standard form right here. It says all of the above mentioned forms of an equation of a line can be put in the form ax plus by equals c for some capital A, capital B, capital Z. capital C, where not both A and B are 0, so there really are variables. This is called the general form of the line, AX plus BY equals C. Sometimes it's called a standard form. I don't like these. I could take one standard form and multiply both sides of this equation by 2 and generate a new equation. It's equivalent to the original equation, but it's got different coefficients. So it's not the original equation. It's equivalent to it, but it's got different numbers involved. Man, all these things are going to be equivalent equations if they represent the same line. But I want to be able to look at it and have a unique representation. And that comes from the slope-intercept form. But there's a standard form. We will play with all of these because it seems to be important to somebody. For me, just ecstatic just to deal with a point slope form. This formula, AX plus BY equals C, we could rearrange it and express it in the form Y equals. So what we're doing is solving for Y here. You know I like the Y equals stuff, so you're not surprised, shouldn't be surprised. I take that standard form thing and start fiddling with it to turn it into my favorite form. Also, I can read slopes and intercepts off easily from my favorite form. So we're solving for Y to get Y equals. We'll take the AX to the other side. It'll become a negative AX. Then we'll have to divide by B to get Y by itself. That will produce, you should believe this. If you don't, pause the video and convince yourself the arithmetic is correct. We'll get Y equals negative A over BX plus C over B. Take the AX to the right-hand side, divide both sides by B. We'll produce this. Well, in this form, that's the slope-intercept form. So, provided B is not 0, we must have a slope of negative A over B. That's the thing that goes here, Zim. And we must have a y-intercept of 0, comma, this thing here. We represented this with a lowercase b previously. Y equals mx plus b. Let's scroll back and take a look at that. Yeah, y equals mx plus b. We've got it in that form. So the slope goes here. The y-intercept goes here. Those were expressed in terms of the capital A, the capital B, and the capital C. But being in those locations, I know I can interpret this as slope and this as a part of the y-intercept as a point at 0, comma, C over B. If A isn't 0, we can find the x-intercept as well. Simply solve for x when you set y equal to 0, and that'll produce the other intercept if you're into that kind of thing. Of course, my problem with this is if ax plus by equals c, I can also multiply through by 2 or 5 or negative pi. I can multiply both sides by any constant and produce another standard form for the line. The standard form for a line is not unique. I don't like that. There's not much I can do about it, except on the test, I can tell you, put your lines in y equals mx plus b form. Put them in point slope form. Makes it easier to grade. We'll work examples now, and in the classroom lectures, we'll work examples and put answers in y equals mx plus b form, because it's the cleanest way to do it. Let's do some examples. Back to exercises. Number 54 says, find an equation for the line with slope m equals -2 and y-intercept 0, -2. Express your answer using the slope-intercept form, smiley emoji, and the general form, frustration emoji, of the equation of a line. So I like the first one. Well, I can easily convert the first one into the second one. So it's not a big deal, but I like slope-intercept form. The instructions in the book want the general form as well. All right. We're given a slope m equals -2. We're given a y-intercept. 0b is how we represented that in the slope-intercept form. We can draw the conclusion that b is -2. So by the slope-intercept form, y equals mx plus b, we've got m is -2, We've got b is also -2. Plug those in, and we get y equals -2x minus x, slope-intercept form. They want us to put this in a standard form or general form. That meant multiple of x plus multiple of y equals constant. So all we got to do is get the x's and the y's on one side and the constant on the other side. Let's take the -2x, take it to the left-hand side. It becomes a +2x. There's a general form. You want to multiply both sides by the square root of 15? I don't know what would possess you, but it's an acceptable general form for the line. But this is the obvious clean way to do it. I like that because it's unique. I dislike that because it isn't. One more time. Let's do another one. Find the slope, y-intercept, and graph the line y equals -3 plus 4. You want the slope and the y-intercept, and this is a piece of cake when the line's in that form. The line's already in slope-intercept form. Y equals mx plus b. M, or the coefficient of x, is -3. Y-intercept is +4. Well, 0, 4. Strictly speaking, y-intercepts come as points, not as just particular values. You may see this dealt with differently in other places, and they might say something like the y-intercept is 4. In this book, they use the point, the y-intercept is the point 0, 4. Of course, if it's a y-intercept, the x-coordinate's 0. So there is some redundance in that, and you might see it dealt with differently in other places. But we get slope is -3, y-intercept is 0, 4 as given. Now you want to draw that. Slope, -3, is delta y over delta x. So find a delta x and delta y that produce a ratio of -3. How about we take the numerator as -3 and the denominator is 1? That'll do. That'll give us a ratio of -3 to 1, or a ratio of -3. With that, we can find a second point. And that's how we'll usually use the slope. Slope is -3. Algebraically, we'll do this as we did upstairs a couple of times. So for another point, we'll take x plus delta x, comma, y plus delta y. We started at the point 0, 4. Okay, 0, 4, right, 0, 4. Delta x is 1, add 1 to the x value. Delta y is -3, add that to the y value. There's the 1 and the -3, the 0 and the 4 from the point are here. That gives 1, 1, the 0.11. So the 0.11 is also on the line. And we got 2 points. We got 2 points, we can find the line. That's all it takes to find a line. So the line must look something like this. To interpret this in a rise over run way, and that's all we've really done, is the algebraic version of rise over run here. We'd say, hey, you got a slope of -3 and you know the point 0.04 is on there. Here's the point 0.04. Let's rise over run equals -3. So how about we rise -3, 1, 2, 3, that is go down 3, and run 1. And that'll leave us here. So that's how I can deal with a rise over run interpretation to produce other points. That's all this delta x, delta y stuff is, an algebraic way of expressing the rise over run to generate more points. 2 points gives us a line. They wanted the graph, and there you go. Another one, find the intercepts of the graph of 3x minus 2y equals 6 and graph it. Okay, they just want the intercepts. To find the x-intercept, we'll set y equal to 0. To find the y-intercept, we'll set x equal to 0. One way of dealing with it. Another way, which is how this is written up, is to use all those formulas we just stated. I'm a little bit better at thinking about stuff than remembering a whole bunch of formulas. So one way to find the x-intercept is to set y equal to 0. So if we set y equal to 0, this would disappear. We'd have 3x equals 6. 3x equals 6 implies x equals 2. That's the thinking way of doing it. The formula way of doing it is saying, well, this line is in a standard form, general form. Ax plus by equals c, where a is 3, b is -2, and c is 6. The x-intercept in those formulas we just saw was c divided by a, comma 0. We've got c is 6, a is 3, 6 over 3 reduces down to 2. So there's the x-intercept from those formulas. I really do prefer x-intercept set y equal to 0, and you find x is 2. 2 comma 0 for the point. For the y-intercept, we had 0 comma c divided by b. Here's c, here's b, do the division, you get 0 comma -3. You got a better way? Yeah, if we plugged in x equals 0, this would disappear, and we'd have -2y equals 6. So y equals 6 divided by -2. 6 divided by -2 is -3. And there's that -3 coordinate. We can also find these intercepts by setting y and then x equal to 0 respectively, as we did in the conversation. But there it is illustrating those formulas. Thinking's better than remembered formulas, in my opinion. You do whatever works for you, though. They wanted us to graph it. All right, we got both intercepts, so let's graph those two intercepts. That gives us 2 points on the line, and there's the line. What's the slope of that line? Well, let's look at the picture and do a rise over run thing. Let's go from this point to that point. It rises 1, 2, 3, and it runs 1, 2. Rise over 1, ratio of 3 to 2. 3 halves is the slope of that line. Wasn't it also, what was it? Negative a over b was the slope. So we'd have -3 over -2, which is also 3 halves. So negative a over b. We had in that formula the slope as well. It's actually probably easier to look at it in terms of rise over run. You remember formulas, it'll come out the same way. No matter how you slice it, the slope of this line is 3 halves. Let's go back to the notes. So next, 2 lines in the same plane are parallel if they don't intersect. Common definition for parallel has to be in a plane. In higher dimensions, things get more complicated. But parallel lines are lines that don't intersect in the plane. If 2 lines in the xy plane are parallel, then they must have the same rate of rise over run. It's rather an informal argument. That means they must have the same slope, and that shouldn't be surprising. Parallel lines have the same slope. We'll state it as a theorem. There's an informal argument for it. We could put together something more rigorous and more confusing probably, but we'll just take this as a given statement. 2 non-vertical lines are parallel if and only if their slopes are equal, and they have different y-intercepts. If I take 2 copies of the same line, they'll have the same slopes. It'll be the same line, but they would intersect everywhere. So that's why they add this little caveat about they have different y-intercepts. We could also say they have different x-intercepts or something in terms of not being the same line is all this highlighted part means. So parallel lines, same slope, parallel lines, as long as the lines are distinct. The motivation for those above comments is look at these 2 lines. They have the same ratio of rise to run. In the pictures, all the pictures we've seen, these have been lines going uphill, lines with positive slope, which is a little bit regrettable. We didn't have more visual diversity in what we did. But these lines are parallel because the rise to run ratios are the same. And by the way, they're not exactly the same line. They don't have the same y-intercept. The y-intercept for this one is right there. The y-intercept for this one, I don't know, this is somewhere down here. It's not there. If it was, we wouldn't have 2 distinct lines. All right, we're almost there. Another example. Find an equation for the line parallel to the line x minus 2y equals -5, which, the other line, contains the point 0, 0. Express your answer using the slope-intercept form and a general form of the equation of a line. Okay. Parallel to this line, we need the slope of this line. We got x minus 2y equals -5. I'm going to get a little stubborn on you and figure this out instead of going back to that A, B, C stuff. Let's rewrite this. Let's solve for y. We'd take the x to the other side and divide both sides next by -2. That would produce y equals +1/2 plus 5/2. The -2 would take care of some of those negative signs. Pause the video if you don't believe it, do the intermediate algebra steps. We'll get y equals 1/2 x plus 5/2. That's an mx plus b form of the line. So slope is this coefficient of x. Slope is 1/2. So this line has slope 1/2. Alternatively, a is 1, b is -2, c is -5, and we have the slope of such a line expressed as, I think it's -a over b. We'd have -1 over -2, which is 1/2. You'd still get the 1/2 out. I prefer this approach to it, but approaches with capital A, capital B, capital C are perfectly legitimate. So the given line has a slope of 1/2. We want a line parallel to that line, then we want a line with slope 1/2. A desired line must have slope 1/2, and they want it to pass through the point 0, 0. Desired line contains the point 0, 0. From the point slope form of the equation of the line, we need y minus y1 equals mx minus x1. Slope, m is 1/2. The point x1, y1 is 0, 0. So the arithmetic won't be very hard. So we get y minus 0 equals 1/2 quantity x minus 0, or simply y equals 1/2 x. There's the desired line. It's got the right slope. It's got the same slope as a given line, and it passes through the point 0, 0, which looking at the equation is easily verified. This reads y equals. This is a slope-intercept form. They want the general form. Let's get all the x's and y's on the same side. So how about we take this to the left-hand side? No, excuse me. Let's take the y to the right-hand side. Then we'll have 1/2 x minus y. We'll have 0 on the left-hand side. Swapping those sides, we'll get 1/2 x minus y equals 0. There's a general form. You want to get rid of that fraction? Let's multiply through by 2. Multiply both sides by 2, and that'll produce x minus 2y equals 0. You want to multiply both sides by something else, you go right ahead as long as it's not 0. And that'll produce yet another general form, standard form of the line. Of course, I like that because that's a unique answer. Either of these is a legitimate answer, along with an infinite number of other things. Back to the notes for one last idea, an idea of perpendicular lines. Two lines which intersect at a right angle, that is 90 degrees, are said to be perpendicular. Theorem 1.3.f, the criterion for perpendicular lines, states two non-vertical lines are perpendicular if and only if the product of their slopes is -1. We'll go through a proof of that. It uses a Pythagorean theorem. Maybe a little comment first before the proof. The above theorem implies that if the lines are denoted L1 and L2, and they have slopes, say m sub 1 and m sub 2, respectively, they're perpendicular if and only if m1 times m2 equals -1. The product of their slopes is -1. This can be rearranged to solve for, say, m sub 1, divide both sides by m2, and we get m sub 1 is -1 over m sub 2. That is, the slopes of perpendicular lines, when you avoid the vertical lines, are negative reciprocals of each other. That might sound familiar. Slopes of perpendicular lines are negative reciprocals of each other. let's go through the proof. Okay, it's based on the Pythagorean theorem. So we have to draw a picture, have to get a right angle in this. First, let M1 and M2 be the slopes of the two lines, kind of as suggested by that note. We can rigidly translate the lines so that their point of intersection is at the origin. We're doing this to simplify some of the computations we're going to do. So in other words, somewhere out there, you got these two lines that intersect. Shift things so that that point of intersection occurs at the origin. Don't rotate things, translate left and right or up and down. So this triangle might have been sitting somewhere over here with a point of intersection here. Slide it over and down. So the point of intersection becomes here. This doesn't change any of the geometry, and it's the geometry we're interested in. And it doesn't change any of the slopes. So it doesn't change any of the algebra either. Does some simplification on the computations. That produces something that looks like this. Take the point A equals 1, comma, m sub 2. Here's the point 1, comma, m sub 2. All right, the slope of this line is m sub 2. We've gone 1 over and m sub 2 up. Of course, the orientation could be different. This is somewhat of a schematic representation, but that's where that line comes from. A rise m2, run 1. Run 1, rise m2 produces a ratio of m sub 2 to 1. The slope is 1. So that's how we get that point A on that line. Similarly, on the other line, run 1 and rise m sub 1. Looks like m sub 1 is negative. Hey, it is. The slope of this line is negative because it's going downhill when read from left to right. So that's why we go 1 over and m sub 1 down, producing the point 1, comma, m sub 1. We've done this before, starting at a point, in this case 0, 0, and doing a delta x, delta y type thing. And the delta x, delta y's were related to the slopes. Delta y over delta x equals the slopes. Two lines with slopes m1 and m2. So this is how we find other points on that line. Go one unit over and the appropriate units up or down to the two lines to produce these points A and B. We started at the origin. Let's call it O. And what we've produced here is a triangle. All right. Pythagorean theorem is going to play a role, and we're going to show that if these two lines have slopes whose product is -1, then this is a right angle. And then we're going to show if this is a right angle, then these two lines have slopes whose product is -1. If product is -1, then right angle. If right angle, then product is -1. Right? The logic goes in two different directions. First, suppose the lines are perpendicular. Suppose this really is a right angle. That means we're dealing with a right triangle. Hey, when dealing with a right triangle, triangle OAB, the Pythagorean theorem applies. We went through this in Appendix A2, and it says this distance squared plus this distance squared equals the hypotenuse squared. The distance from O to A, that's the length of this side, plus the distance from O to B, length of this side squared, equals the hypotenuse, the distance from A to B squared. Informally, we usually refer to the Pythagorean theorem. I don't care much for this, but you might think of it as A squared plus B squared equals C squared. This is A, the length of one leg of that right triangle. This is lowercase b, the length of another leg of that triangle. And this is the hypotenuse, C. Not to be confused with the capital A, capital B stuff that we've introduced here. But it says the sum of the squares of the legs of the right triangle equals the square of the hypotenuse. So there's a Pythagorean theorem. It works if we have a right triangle. We've assumed we have a right triangle. We've assumed the perpendicularness in this part. Point O, we had coordinates for it, was the origin. Point A was 1 comma M2, and point B was 1 comma M1, as discussed with an interpretation of slopes on those two lines. So we can find the distances. Actually, let's find the distance squared. We find the distances, we use the distance formula, and we have to take square roots. Let's just find the distance squared. That's what we need. That's what the Pythagorean theorem requires. Distance from origin to point A would be change in the x coordinates, 1 minus 0, 1 minus 0 squared, plus change in the y coordinates, m2 minus 0 squared. That simplifies to 1 plus m sub 2 squared. The zeros are easy to deal with. The distance from the origin to B, 1 minus 0 squared, m1 minus 0 squared. Zeros make the arithmetic easy again, and this time we get 1 plus m sub 1 squared. It's right, the very similar format. Distance from A to B, a little bit more complicated, would be change in x coordinates, 1 minus 1 squared, plus change in y coordinates, m2 minus m1, say, squared, or m1 minus m2. Order really doesn't matter in this one. We're squaring, and any negative signs gets absorbed in this. So 1 minus 1 is 0, we lose that. Square this out, we'll get first one squared, minus twice the product, minus 2m1, m2, plus the last one squared. So there's those three distances. All right, we're trying to show, assuming a right angle, the product of m1 and m2 is negative 1. The product of the slopes is negative 1. What's this got to do with anything? Well, we know from the Pythagorean theorem that this thing plus that thing equals this other thing. The length of the leg of one, the length of the leg of one of the legs in that right triangle plus the length of the other leg squared equals the length of the hypotenuse squared. This square plus this square equals that thing, equals this square. This plus this equals that. The squaring has already been compensated. This is what we had from the Pythagorean theorem on the previous slide, so we'll plug this stuff in. Distance from 0 to a squared is 1 plus m sub 2 squared. This distance, 1 plus m sub 1 squared. This distance, that thing. Okay, so we'll write that out. Let's simplify. We get 1 plus 1 is 2 plus m sub 2 squared plus m sub 1 squared. Right-hand side, oh, we can cancel some stuff. Let's see, there's a m sub 2 squared on this side and that side. There's an m sub 1 squared on both sides. Subtract those out. That'll leave you with a 2 on the left-hand side and a negative 2 m1, m2 on the right-hand side. Divide both sides by negative 2. They will be left with m1, m2 on one side and negative 1 on the other side. m1 times m sub 2 equals negative 1. That's what we were trying to show. So if those lines intersect at a right angle, then the product of the slopes of the two lines is negative 1. We're halfway there. Now we need to show if the lines satisfy this algebraic relationship with their slopes, then the lines intersect at a right angle. And it's basically this argument backwards. We want to go from this assumption to the conclusion of right angle. Now suppose m1 times m sub 2 equals negative 1. We're reversing the previous argument, basically. This is an exercise in this section of the book. Well, you can't argue with the following. Then let's multiply both sides by negative 2. Then we'd have negative 2 m1 m2 equals positive 2. We'd get this out. Can't argue with the validity of it. Why would you want to do that? So we're trying to do the last thing backwards. So previously we divided by negative 2. Here we're multiplying by negative 2 to produce this. How about we add m sub 2 squared plus m sub 1 squared to both sides of this? Why? Because I'm trying to undo what we had before. But we've added the same quantity to both sides. Let's rearrange that left-hand side in a suggestive way. Hey, that picture we had, didn't assume we had a right triangle when we went through and labeled those points and found those distances. That's the distance from the origin to point A, distance squared. That's the distance from O to point B, distance squared. And this is a distance from A to B squared. So in that triangle, we have one side squared plus the length of another side squared equals the length of a third side squared. That only happens in a right triangle. That's the converse of the Pythagorean theorem. Theorem A.2.b, to refresh, states that we have a right triangle only if the square of one side is the sum of the squares of the other two sides. The square of one side is the sum of the squares of the other two sides. Triangle OAB then is, by the converse of the Pythagorean theorem, it's a right triangle. If it's a right triangle, then those lines intersect at a right angle. That is, the lines are perpendicular, and that's what we were trying to show in that claim. So Pythagorean theorem and its converse allows us to establish this idea of negative reciprocals for intersections of perpendicular lines. So of course we want to illustrate that. Let's look at a couple of questions that intersect that illustrate that, and then a couple more exercises to wrap up this section. Okay. Find an equation for the line perpendicular to the line, y equals 2x minus 3, which contains the point 1, negative 2. Express your answer using the slope-intercept form, yay, and a general form of the equation of a line. Okay, they want it perpendicular to this, and they want it to contain this point. We need a slope for our desired line. Well, what's the slope of this line? Y equals 2x minus 3. It's already in slope-intercept form, y equals mx plus b. So m must equal 2. The slope of this line is 2. But it ain't this line that we're interested in. We're interested in a line perpendicular to this line. We want the negative reciprocal of this for our desired line. The desired line must have a slope of a negative 1 over this m value. That is, negative 1 over 2. This is the slope of, as I'm calling it throughout this, the desired line, the one they ask us to find. Desired line has this slope. We were told to make it contain this point, 1 comma negative 2. Well, then we've got a slope and a point. Let's use the point slope formula, which says y minus y1 equals m quantity x minus x1. We've got the x1, y1 as 1, negative 2, respectively, and we've got the slope of negative 1/2. So plug the negative 2 in for y1, goes there. Here's the negative 1/2 m, x minus x1. We've got x1 is 1, plug that in here. That produces this. I could quit there, I suppose. But they want it in a particular form. I kind of agree with them on that first one. So let's simplify this a little bit. Y minus negative 2, that'd give us y plus 2. Take that plus 2 to the other side, and it would become a minus 2, if you like. Negative 1/2 x minus 1, I simply drop some parentheses. Solving for y by subtracting 2 from both sides produces this. We've got it reading y equals, so I like that. That's very slope-intercept-ish. Do the arithmetic. Negative 1/2 times x, negative 1/2 x. Negative 1/2 times negative 1 is positive 1/2. We still got the negative 2 on the end. 1/2 minus 2 is negative 3/2. That produces this on the right-hand side. Slope, y-intercept, by the way. Slope-intercept form is y equals this, negative 1/2 x minus 3/2. Slope-intercept form, there's the slope, there's the intercept of the desired line. And now they want that in some standard form, also known as a general form. Okay, let's take the x term to the other side. That'll give us positive 1/2 x plus y. equals -3/2 is still left on that side. That's an acceptable form. Well, we could multiply through by +2 to get rid of the fractions. This would become a coefficient of 1. The y would pick up a coefficient of 2, and the right-hand side would lose that divided by 2 part to leave us with x plus 2y equals -3. Then you can multiply both sides by something else as long as it ain't 0 to produce other general forms. This is the most natural one. It involves the simplest numbers. This is the unique slope-intercept form of the desired line. Another one asks us, determine whether the lines y equals 1/2 x minus 3 and y equals -2x plus 4 are parallel, perpendicular, or neither. I claim it's pretty easy. We need to find the slopes of both of these lines. And we need to see if those slopes are the same for parallel, negative reciprocals of each other for perpendicular, or none of the above. Is it easy to find the slopes of these two lines? In this form it is. It's just the x coefficient. This is in y equals mx plus b form, and so is this. So if we let the first line, call it L1, have this equation, the second line, call it L2, have this equation, then it's easy to read the slopes off. The first slope, m sub 1, is the coefficient of x because it's in y equals mx plus b form. Pick the coefficient off to get a half. This one, coefficient's -2, so the slope is -2 for that one. First one has a slope of 1/2, second one has a slope of -2. They're not equal to each other, so with theorem 1.3.e, criterion for parallel lines, the lines aren't parallel because their slopes are not the same. If you multiply the slopes together, multiply 1/2 and -2, that produces -1. Oh, they are perpendicular. The product of the slopes is -1. One is the negative reciprocal of the other. So the lines are perpendicular. It was theorem 1.3.f specifically that gave us that, the thing we just went through the proof of. So let me sing the praises again of y equals mx plus b, point slope form. I'm sorry, slope-intercept form. It's easy to read the slope off when it's in y equals mx plus b form. So here's a reason to like that. I like it because it's easy to tell what the slope is, and I like it because it's a unique representation of the line. There's only one slope-intercept form for the equation of a line. All right, something related to that same idea. Says use slopes to show that the quadrilateral whose vertices are these 4 points here is a parallelogram. All right, parallelogram. That's a four-sided figure with opposite sides parallel. Let's plot the points. Easy enough with my clicker here. 1, -1, 1 unit over, 1 unit down, first point. 4, 1, 4 units over, 1 unit up. 2, 2, 5, 4, 5, 4. So there's the 4 points. Let's connect them so that we see the quadrilateral. They say, show this is a parallelogram. So we need to show these two sides are parallel and these two sides are parallel. How are you going to do that? By finding the slope of a line through these 2 points and finding the slope of a line through these 2 points and showing those slopes are the same. And similarly for the other part. So slope of the line segment joining 2, 2 and 5, 4. Let's see, 2, 2 and 5, 4. That's the upper one. Is change in y over change in x. y2 minus y1 without all the labels, 4 minus 2. x2 minus x1, 5 minus 2. Notice the 4 and 5 correspond here because they're together here. Notice the 2 and 2 together there corresponds here. Corresponding coordinates in corresponding positions in a sense. 4 minus 2 is 2, 5 minus 2 is 3. So we get a slope of the top part of 2/3. the slope of the line joining 1, -1, and 4, 1. 1, -1, and 4, 1. All right. Similar computations. 1 minus -1, y2 minus y1, 1 minus -1, x2 minus x1, 4 minus 1, substituted in here. I won't bore you with all the arithmetic. Feel free to pause and double check. We also get 2/3. Hey, those slopes are the same. So these line segments are parallel. Let's check the other two sides. The slope of the line segment joining 1, -1, and 2, 2. That would be this line segment is, you get the idea, use a slope formula, we find a slope of 3. Does that make sense? You rise 3 and run 1. Yeah, it makes sense. Same thing happens here, right? Rise 3, run 1. Yeah. Formally, the slope of the line segment joining 4, 1, and 5, 4, 4, 1, and 5, 4, this one is, do the computations, it's also 3. So these two line segments are parallel as well because they lie on lines with equal slopes. Let's state that formally to get the answer in front of us. M1 equals M2, criteria for parallel lines, tells us that it was the top and the bottom are parallel. M3 equals M4, same result, tells us the left and the right are parallel. That is, this quadrilateral is a parallelogram, just based on the fact that parallel lines have the same slopes. One last application says, a report in the Child Trends database indicated that in 2000, 20.6% of 12th grade students reported daily use of cigarettes. Wow. In 2012, 9.3% of 12th grade students reported daily use of cigarettes. Not me to question how accurate the numbers are. They say, write a linear equation that relates the percent Y of 12th grade students who smoke cigarettes daily to the number X of years after 2000. Okay, so we got an X and a Y. We got 2 points, which will have to be carefully interpreted. X is the number of years after 2000. Well, in 2000, that's 0 years after 2000. X equals 0 and Y equals 20.6%. What's up with this year and percentage? The X coordinate would be 12. This is 12 years after 2000. And the Y coordinate would be 9.3%. So according to their scheme, they've given us 2 points. They want a linear equation, not a problem. 2 points determine a line. In terms of X and Y, appropriately interpreted the X values especially. Write an equation, part B, find the intercepts of the graph of your equation. Part C, do these intercepts have meaningful interpretation? Part D, use your equation to predict the percent for the year 2025, for which X would equal 25. That's 25 years after 2000. Is this result reasonable? So they try to make you think a little bit in this one beyond just algebraic manipulations. Okay, we're given x1, y1 equals 0, 20.6. 0, right, 0 years after 2000, that's how the X's are measured because they said so. Keep the numbers a lot simpler. And a Y value, a percent of 20.6, okay? And 12, 9.3. This is 12 years after 2000 for the X value and 9.3 for the Y value. So these are 2 points on the desired line. So the slope of the desired line is change in Y over change in X. Say 9.3 minus 20.6, change in Y over corresponding change in X, 12 minus 0. Simplify, we get negative 11.3 over 12, which I don't like approximating, but that's the intent of this question. Negative 11.3 over 12 to 3 decimal places is negative 0.942 approximately. To 3 decimal places, we get that. So there's a slope. By the way, it's negative. So that tells you this relationship is, when we graph the line, it'll be going downhill. That's how we set it. What it really means is as time goes by, this percent decreases. Since the point 0, 20.6 is on the desired line, then from the point slope equation for a line, we have y minus y1 equals m minus x1 point slope form. We've got a slope, it's an ugly number, negative 0.942. We've got the point x1, y1, so we'll plug 0 in for x1, 20.6 in for y1. That produces this. When you multiply out and simplify, it produces this. So distribute and then do the arithmetic. Take the 20.6 to the other side. So that simplifies fairly clearly to this. So there's the linear equation that relates x and y. There's y in terms of x. Okay, we'll need this next. So we'll reproduce that. I've also reproduced the question on this slide. They want to know the intercepts. Okay, we'll set y equal to 0 to find the x-intercept. So we'll get a 0 here equals negative 0.942x plus 20.6. Solve that equation. Take the 20.6 to the other side and divide by this coefficient. That'll produce negative 20.6 divided by the coefficient for the x value. Set y equal to 0, solve for x. Calculator gives me 21.868 to 3 decimal places. So we've got when y equals 0, x is roughly this. That's the x-intercept. To find the x-intercept, set y equal to 0. To find the y-intercept, set x equal to 0. With x equals 0, this drops out and we get y equals 20.6. So that gives us the y-intercept. Again, these are written as points, so they come to us as ordered pairs. There's the x-intercept. There's the y-intercept. That takes care of part B. Part C, do these intercepts have meaningful interpretation? They do. The meaning of the y-intercept, 0, 20.6, is that when x equals 0, that is in the year 2000, y equals 20.6%, that is 20.6% of 12th grade students reported daily use of cigarettes. The meaning of the x-intercept, 21.868, is that in the year 21.868, so you got a typo here, it should be 2021.868. I don't know where these numbers came from. When x equals 21.868, that is in the year 2000, 21.868, excuse me. I don't know where those numbers came from. Probably I messed up arithmetic the first time I worked it. We'll have 0%. At that x value, we'll have 0% of 12th grade students reporting daily use of cigarettes. If we assume this linear model. So in the year 2021.868, which is about now when I'm recording this, it's late 2021. If we follow that linear model, then 0% of this 12th grade student should be reporting daily use of cigarettes. That would be the interpretation of those intercepts. Assuming a linear model is definitely a simplification of what may be real. Part D, they say, use your equation to predict the percent in the year 2025. So that'll be when x equals 25. Here's the formula. In 2025, x equals 2025 minus 2000. That's x equals 25. So the percent for the year 2025, we'll plug x equals 25 into the formula and see what happens. We get y equals negative 0.942 times 25 plus 20.6. Do the computations, you'll get negative 2.95. Mindlessly plowing ahead. This would be interpreted as claiming that in the year 2025, negative 2.95% of 12th grade students would report daily use of cigarettes. Is this reasonable? No. I mean, the smallest percent it could be is 0. So negative 2.95% doesn't make any sense. A negative percentage, it's not meaningful in this setting. So this is not reasonable. No. You've oversimplified things. You've taken 2 points, assumed a linear model, and that's all we can do with what we know at this stage. And you've tried to extract from that. And making predictions into the future or the distant future, assuming some elementary model, that's not a good idea. This is certainly nonsense. This just doesn't make sense at all. So you have to be careful when modeling, when you try to extrapolate from models. Interpolation, maybe that's a different thing. You want to talk about what happened between the year 2000 and the year, I forget what the second year was. You want to go between those 2 years and use a linear model. Maybe there's reasons to think that is reasonable, but extrapolating from that is unreasonable. We could run this backwards in time and probably find something along the lines of, in the year 1980, over 100% of high school 12th graders were smoking on a daily basis, and that's meaningless. It can't be more than 100% or less than 0%. So be careful when applying models, is kind of their angle on this one. And that takes care of the last example from this section. So there's a lot of stuff about lines. In the next section, we'll look at circles and talk about equations of circles and radius, and we'll graph some circles based on centers and radii. I will see you there. Have a nice day. See you in section 1.4.